As you are seeing that you are able to see my screen, so now we can start. So as in the previous class someone said that some questions apart from the that courses is also required for your other purposes such as test exam. So that's why I just prepared some classic questions where that these questions could help you to in those exams. So we will solve those questions today in this today's tutorial. So I hope you guys just hear me as well as you can see my screen now. So the first question, if you can't see or you can hear me, just stop me there and ask, just say me that you can share, or you can use the chat box to say me something and ask me some questions. So that's that. Now now today's first question is that heat flows radially. Suppose a system is there where heat flows radially outward through a cylindrical insulator of outside radius r1. So let me copy this question first. Okay. We'll solve it here in solution. Okay. So now what it is asked, it is asked here, a heat flows radially outward through a cylindrical insulator of outside radius r2 surrounding a steam pipe of outside radius r1. The temperature of the inner surface of the insulator is T1 and the temperature of the outside surface is T2. At what radial distance from the center of the pipe is the temperature is exactly halfway between T1 and T2. So that means there are two cylindrical pipe is there whose this radius is r1, small r1, small r1, small r1, and there is another cylinder whose radius is r2. Now this question is not directly related to the statistical mechanics, it's actually a question from thermodynamics, but since in the previous two lecture and the tutorial we are dealing with these thermodynamic relations and those things, so it is a good thing to recap those things here. So that's here, this is a cylinder and this is the insulator, inside this is insulator and this is a insulator surrounding R2 stem pipe and outside radius R1, this is R1 and this is R2. The temperature of the inner, so the temperature of the inner surface here is T1 and the temperature of the outer surface here is T2. Now to solve this type of question we have to first assume that the heat is flow towards any direction, it can be any direction, and that the heat capacity is K. So we know that the heat flow through dx, there is a suppose a medium is dx, dx and its area is A, then the heat flow through this that chunk of this conductor is equal to K dx A, and in time dt the heat flow will be dq equal to like this, so that it can be written as k capacity A dx dt, right? Now here for the cylindrical case, what is the surface area? A will be 2 pi r into the length of this cylinder, so 2 pi r into L. R is the radius. Suppose I construct a surface here whose radius is r and its length is L, so area is 2 pi rl. So that means K into 2 pi rl, and in the question it is asked, it is said that the heat is flow radially outward. That means the dx is dr actually. So So that means dx is dr, so 2 pi r l into dr by dt. Maybe I'm doing something wrong, let me check it. Yeah, so I'm doing what is the wrong, so that is the wrong thing I'm doing here, so sorry guys. So if the temperature gradient is dt here, it is not time actually, if the temperature gradient is dt and big T is dt, suppose that it is dt. Okay, let me do it properly. So suppose that there is a chunk of conductor whose cross section area is a, and the width of this conductor is dx, and the cross section area is a, and if some amount of heat flows through this conductor, then the amount of heat is flowing through this conductor, amount of heat flowing through this conductor at time dt is dq dt will be minus capacity A into the cross sectional area A into the temperature gradient, which is dt, and by the width of that chunk of this conductor. So now here it is said, as I am saying, that it is in the question it is asked that radially outward the heat is flow through radially outward, that means dx is nothing but dr, dx is nothing but dr, and what is a is equal, a actually is 2 pi r l. So if I put it here, so it is, so this is basically q dot is nothing but dq dt minus k into 2 pi r l dt dr. Now from the algebra we can know that from this simple we can do it, dt equal to q dot minus k into 2 pi r l dr. I just did nothing, I just integrate it over dr, integrate both sides over dr, and I take this factor just in the lower side of these things. So then if we integrate again, dt is equal to minus q dot by k 2 pi l integration dr by r. Now you can see that what I am going through this calculation, that I am actually want to calculate what is the temperature difference, between this cylindrical surface and this cylindrical surface. Suppose here the temperature is T, and we know that here the temperature is T1. So what is the difference T1 minus T2, T1 minus T is? So that I am want to calculate. So that's why I integrate out, and dr is nothing but, so that means T1 to T is equal to R1 to R. I have to integrate it R1 to R. So what it will give? It will give me nothing, T minus T1, nothing but T1 minus T minus T1 minus q dot by k 2 pi l into is ln r minus ln r1. Okay, now these things we don't know, right? This q dot by 2 k 2 pi l we don't know, but let's see that what information is given in this question. That one information is given that the temperature of the inner surface is T1 and that the outer surface is T2. We actually know the temperature of the outer surface, so we will use this information to get rid of this factor. So since it will follow the same formula, from the same formula we can now write T2, we can now write T2 minus T1, where the temperature is T2 at R equal to R2. So let's put it there, So minus q dot by 2 pi kl into ln r2 minus ln r1. So now if I divide this with this, we will get t minus t1 by t2 minus t1 is equal to, now you can see that we can get rid of this. We can now, if we divide t minus t1 with this, then we actually get rid of this factor. So now what we will get? We will get ln r minus ln r1 by ln r2 minus ln r1, which is nothing but ln r by r1 minus ln r2 by r1. Now what is asked in this question? Now it is asked, what is asked? Okay, who is there? Hello, Mr. Lakshmi, can you? Okay, that's there. So what is asked here? The question is that what is the radial distance? Means we have to find the radial distance r, where the temperature will be just halfway between T1 and T2, which is we have to calculate what is the r, for which temperature T will be T1 minus T1 plus T2 by 2. So what we'll do, we'll just put T here and we'll extract the for what value of r it will satisfy. Let it there, put it there. So T minus T1 will be T minus T1 plus T2 by 2. Sorry, T is here minus T1, right? T minus T1, so T1 plus T2 minus 2T1 by 2, it is actually T1 T2 minus T1 by 2. Okay. Now if we put it there, that means we will get, so T2 minus T1 by 2, T2 minus T1, and we have to extract this information. So ln, suppose that r equal to r prime, this equation will satisfy. So r prime by r prime by r1 by ln r1, so r2 by r1, right? R2 by r1, so that means ln r prime by r1 is equal to, this will be nothing but half ln r2 by r1. So I can put it there, ln root over of r2 by r1, right? Now what is the r prime by r is equal to root over of r2 by r1. Mr. Lakshmi, can you put it here? Hello? Okay. Yeah, Muktu Lakshmi, do you want to say something? I don't know. So the radius will be r equal to r1 into root over r2 by r1. So it will be actually root over r2 by r1. So that means at what radius, now we have calculated these things, at what radius the temperature will be exactly T equal to T1 by T2 plus half, which is actually r prime is equal to root over r2 by r1. So at this radius the temperature will be just exactly halfway between these two surfaces. So this is the first question we have done with, we just calculated. So if you have any question regarding this question, you can ask me now. or otherwise I will go to the next question. So let's go to the next question then, if there is no. So the next question, let's copy the next question. Okay, so okay, now in this next question it is asked that the adiabatic lapse rate, that means the variation of temperature in the atmosphere as a function of height, may be explained by adiabatic expansion. How it is adiabatic expansion? Now the air near the surface heated due to sun's radiation. So at the surface of this atmosphere, that air is actually heated by this direct radiation of these suns, and it's also heated from the below. Means it's the, if it is the atmosphere, I mean if it is the earth, then this surface actually heated by the direct radiation of the sun, and just above the earth surface the air will be heated by this radiated, just reflected back radiation, the radiation that is reflected from this earth surface. From this heat, this air just got heated. Now since this air got heated, that means it's since we know that the hot air actually has a lower density, that means it will go upwards. So that means hot air from the lower region rises to upwards. Now there will be a lower pressure, since there is low amount of air is there, so that means the pressure will be high, pressure will be low here. Now therefore the air between these will be expand. Now it expands, since the air is this air actually surrounded by this air, and we know that the air is poor conducting medium as a heat. So that means the heat cannot be flow from this region to this region, and since the pressure is low here, so it want to expand. So this region want to expand. So that means this expansion can be approximately thought as the adiabatic expansion. Now what we will do, we will assume something, that our first assumption will be this air actually ideal. If we assume that this air is ideal gas, that means this follows the ideal gas equation, PV equal to RT, or maybe I can write it PV equal to NKT in KT. Okay, then now if we apply the first law, first we have to calculate the expression for this, how this gas will be expand when in the adiabatic. What means in the adiabatic expansion, what kind of thermodynamic relation it will hold. So we actually know that PV to the power gamma equal to constant. It is the state followed by a gas which is in thermodynamically adiabatic. In the if we expand or contract the gas adiabatically, it will actually follow this state, this thermodynamic relation. So let's first derive this thermodynamic relation, then we will just apply this relation to the first law, and we will actually can calculate, since it is it is asked to calculate the temperature gradient per height, dt dh. If h is the height and t is the temperature, so what is the value of dt dh? So to calculate this, we need this relation. So first we have to, okay, so let's first derive this relation. So from where we derive this relation, let's see. So we know the first law of thermodynamics. So first law of thermodynamics says dq equal to du plus pdv. Now for specific heat Cv with volume constant, we know that it is actually del u del T. Actually here Cv will be del Q del T with volume constant. If we keep volume constant, then means this term will go 0, so du dt. So this relation can be rewritten as dq is equal to Cv dt plus P dv, and we know that dq is actually 0 for adiabatic process. dq is equal to 0 for adiabatic process. Adiabatic process. Now that means 0 is equal to Cv dt plus pdv. So and another relation is pv equal to nkt. So if we applied here, we will get 0 is equal to Cv dt plus P. In place of P, if I put it, P is equal to nkt by V. So nkt by V dV. So it will be minus Cv into T. Okay, let me do it. So if we integrate out, then we will get Cv into T plus nkt to ln V is equal to constant. Now we can write it as, okay, so T plus, so this, okay, let me check it where I just, oh I just got it wrong here. So this will be minus Cv dt by T is equal to nk by V dV. So this will be minus Cv ln T nk ln V plus some constant. That means we can write it here that ln T plus nk by Cv ln V is equal to some constant. Now from another things we can, this is actually and the gamma, as we written here, the relation will be, we need the relation, this type of relation Pv to the gamma, and here the gamma is nothing but Cp by Cv. So let's calculate the relation, another relation of Cp Cv. I know that you already know all these things, but for the recap I actually want to derive this, what is the relation between Cp and Cv. So let it do it from here, that del, if it dq, we know that dq equal to du plus pdv. If I dq, if I derivative it with respect to temperature with pressure constant, so this will remain constant Cv dt. So this plus P del V del T. So it's nothing but, since we know that U is equal to Cv dt, du equal to Cv dt, so it's this du does not depend on the pressure. So that means this can be straightforward write as, we could write this as Cv plus P del V del T. From this relation del V del T with pressure constant, del V with pressure constant del V del T, from this relation, okay, from this relation V is equal to nkt by P. Now del V del T with constant pressure will be nothing but nk, right, nk by P, okay, nk by P. Now if I put it there, nk by P, that means and it is nothing but Cp. So Cp, that means Cp minus Cv equal to nk. So from here, that means So nk, in place of nk, if I put Cp minus Cv, then we will get what ln T plus Cp minus Cv by Cv into ln V is equal to constant. That means T plus Cp by Cv means gamma. So ln T plus gamma minus 1 ln V is equal to some constant. That means T p to the power gamma minus 1 is equal to constant. Now from this relation we need the relation between the pressure and temperature. So extract that relation from the pressure and temperature. Let's again apply the state equation of the ideal gas. If we apply that, so we know that PV equal to NKT. That means in place of V, if we put the relation of P, we will get NK to the power gamma minus 1 T to the power gamma minus 1 by P to the power gamma minus 1 is equal to come constant. So that means if we invert it, 1 minus gamma T to the power gamma is equal to constant. So actually we need this relation, P to the power 1 minus gamma T to the power gamma equal to constant. Now let's see what can we do from this relation. Now so from here we can write this expression, its differential form as differential form. If we take ln, if I take the both side ln, it will be 1 minus gamma P plus gamma ln T is equal to again some constant. Now its differential form will be nothing but dP by P plus gamma dt by T is equal to constant. Now the thing is, now let's apply some physical thing here. Now what is the pressure? Since we have to calculate the dt dh, that means we have to extract the pressure in terms of the height. So if we know that this is a cylinder in the atmosphere, if the density of the gas molecule here is rho and height of the cylinder is h and the surface area is a, what is the pressure? Pressure will be nothing but the force by the area acted on this surface. What is the force? Force is nothing but the total weight of this gas molecule inside this cylinder. So what is the weight will be this gas molecule? Weight will be the mass will be density into the volume. Volume is area into h, that is the volume, that is the mass of the things, and weight will be multiplied by the g. And so, and here of course we assume that g is uniform throughout this height. So that means P, we can write P equal to F means rho A H G by A, which is equal to rho H G. Okay, now we can write dP as rho G into dH, and we know that PV equal to okay, let me write it here. We know that PV equal to NKT. That means P means N KT by V, that PV by P will be rho G, okay, rho G dH. P will be N KT by V. So rho V into G by N dH by KT. Okay, dH by KT. Okay, write it properly now. So this will be rho into V will be up by N is there, G is there, by K dH by T. Now you can notice notice that this is rho into V is nothing but the mass of that mass of the gas molecule here, and n is the total number of molecules there. That means the weight of a single gas molecule, m by n, what it signifies? It signifies that the mass of a single atom, the n atom, if I put n atom here, its total mass will be rho V, and then per particle mass will be m by n. So m by n into g by k equal to dH by t. So if I put dP by p here, 1 minus gamma m by n g by k, dP means dH by t plus gamma dt by t is equal to sum. It is actually 0, not constant. Here it is constant, but when I just differentiate, it becomes 0. So that means it becomes 0, which keeps us, if I take this, what we have to calculate? We have to calculate dTdH, right? The adiabatic lapse rate dTdH. So the temperature gradient dTdH. So dTdH means 1 minus gamma m by ng by k dH m by k. Yeah, Madhubala, you want to ask something? Hello, Madhubala, if you want to ask something, you can ask me. Okay, if there is no question, then I can proceed further. Okay, so dH will be dH equal to minus gamma dt. So that means dt dH will be minus 1 minus gamma by gamma into m by n g by k. Now you can see that since the gamma is always less than 1, since this relation holds, at that means we actually calculate the gradient of the temperature. If I just rise, I just okay, let me check one thing. Okay, so here I just did one silly mistake. That means when I just increases my height, that means from the ground I just increases my height by amount dH, my pressure will not increase, my pressure should decrease. That means that information should contain in this differential thing. So that means dP should be negative rho gdH, means if I increase my height from the ground dH, the pressure would be lower by amount rho g into dH. So that means this negative sign should be there. That means dP by p, their negative sign is there, negative sign is also here, negative sign is there, sign negative, that means here positive. Since now we know that gamma is always greater than 1, that means negative gamma minus 1 by gamma into m by n g by k. Okay, that this physically tells us if I increase my height from the ground, the temperature of the atmosphere should decrease, because this is a negative. That means the gradient should be negative. That means as I increase my height from the ground, then the temperature should be lower and lower. So this relation actually tells us, and we actually solve this question, and the answer of the question will be, what is the temperature gradient? Temperature gradient will be dt dH is equal to minus gamma minus 1 by gamma into m by n g by k. So that's it. Now If you have any question regarding this question, you can ask me, or I can, or otherwise I can further proceed to the next question. Okay, if there is no question, then I can proceed further. Now my third question. Okay, so this third question is very simple. So here it is asked that all natural processes are irreversible. So this question is directly related to the first class, where in the tutorial I have tell you guys that about entropy. Yeah. So it is directly related to that tutorial, and there is also a question also there. So this question is actually directly related to the first lecture of this lecture series. So all natural processes are irreversible. Okay, this is a direct consequence of the first law of thermodynamics. So after going to solve, so before going to solve this question, I want to spend some time to introduce the concept of irreversibility. So this is actually very interesting thing, that classically, or classically all the things can be derived from this Newtonian's law, and the Newtonian's laws actually all are reversible in nature. That means if I time reverse the system, it will exactly, suppose write that we know that the revert dp, p is the momentum, dt is actually f, force. Now if I time reverse the system, that means if I just going backward in time, we should always reach to the initial condition from where we just started. It should always satisfy from the premise of this Newtonian mechanics. Let's see that if I put t2 minus t, that means dp will be nothing but, okay, no, it's not this. Okay, let me. So is actually dx coordinate, d2x, dt2, x is the position, so this is actually f. So if I t goes to t minus t, it will dx, that if I go, the t goes to t minus t, that means dt of dx dt will be here one negative sign, because of t goes to dt, and there is always another negative signs. So that means overall there is no negative signs at all. So that means my equation of motion d2x dt2 should always remain valid. That means this system is actually reversible. This system actually reversible. Reversible. This tells us that if we can derive all the things from this Newtonian mechanics, then all the things that we see in nature should remain reversible in nature. If I exactly backward the system should reaches its initial conditions, reach to the initial condition. But this is not the case in the nature, as the second law says that the all natural process are actually irreversible. So this is the nature follows this law. So it's actually quite unintuitive, because from the Newtonian mechanics we actually know that all the systems should be reversible in principle. But where this irreversibility comes, it's actually a question of the research. So this is actually not actually well known to us. So from where this irreversibility comes, one of the thing is classically one of the thing is chaos, and a large range of research is going on to know the exact cause of this irreversibility. So that's that. Now in the question it is asked that all natural processes are irreversible. This is a direct consequence of, so first law of thermodynamics, no, first what first law of thermodynamics says? First law of thermodynamics says energy equivalence principle. It says that you can't destroy energy, or you can create energy, or you can't create energy out of nothing. So the first law of thermodynamics doesn't tell us about irreversibility. Now the second law might be, second law can tells us something about irreversibility, because second law is saying that in every process the entropy is increasing, right? The entropy is increasing means, if I reverse the process, I will not reach to the same initial conditions. That means the second law actually tells us about the irreversible nature of the natural process. Let me show you that ds should be 0 in any process if I put the if I just change the system in the forward direction from A to B, and now if I take the system from B to A, the entropy should remain 0. If the system is reversible, I just put back to the system in the same initial condition, so the ds should be 0. But as we observe in nature, the ds, this happens if the thing is reversible, if this thing is actually reversible, if this process is reversible, then the entropy should be 0. But as we observe in the nature, in every process, when we just put it back here, they will come back in the initial position, the entropy actually increases by some amount. So that means this is actually indicating something about the irreversibility of that every natural thing. So that means entropy, or that means the second law of thermodynamics actually says about the irreversibility of the system. So the answer of this question will be the second law of thermodynamics. Second law of this is second law of thermodynamics actually is a the natural, all natural processes are irreversible. This is a direct consequence of second law of thermodynamics. Now it's actually solved question now, but for the pedagogical purpose we also know what is third law says. Third law says nothing but about it actually says at temperature 0, at T, if T goes to 0, then entropy should also go 0. And what is the Gibbs paradox? And we also know the Gibbs paradox actually. So Gibbs paradox means if there is a ideal gas, and suppose I put an imaginary wall between this gas, that means there is a two part of the gas is produced. Now we know that mixing means if there is a huge number of particles are there, and if we mix homogeneously the two set of particles, then we cannot then we cannot separate it out. That means the entropy is increased in the mixing entropy always increase, right? Always increases. But if I just remove this imaginary wall from here, then the system remains the same. That means the entropy should not be increased by the same amount. This actually poses a paradox which is called Gibbs paradox. So now let's move to the next question. Next question is, suppose that a piston containing an ideal gas is originally in the state X, okay, the gas is taken into a thermal cycle x to y and again y to x. Okay, now the work done by the gas is positive if the okay, this is P, this is V, if the direction of the thermal cycle is clockwise, counterclockwise. Let's check. So if I move from x to y following this path, means this way, what amount of work we have done? This much work we have done. The area under this curve, because the work is nothing but PdV. Integration of PdV is the total work. Integration of PdV means the area under this curve. Okay, fine. So that means if we move from x to y in this direction, that much work we have done. The W1 is, this is W1. Okay, now if we again go y, from y to x, how much work we have to do? We have to do the area under this curve. The area, what will be the area under this curve? Area under this curve will be this much. So here, so how much energy, how much that much work we will get, right? So how much work, the work done by the gas is positive. So here this much work is done, and we have, if we want to increase the volume of this gas, that means we have to give some work to the system. We have to do some work on the system. That means the total work done by this gas is actually W1 minus W2. Now from here you can see that this blue region is actually less than this green region. That means it is always negative. That means if we go in this direction, we can't extract any work. That means the gas will not do any positive work. It's always remain negative. So now if we, this is actually counterclockwise, right? Now if we go clockwise, so let me draw it again. So now if we go clockwise, this P is V, this is X, this is Y. Now if we come clockwise, this means if we reduce the volume, by in this path, how much work we have to do? That much amount of work we have to do, the area under this curve. Now again we reach this point. Now if we want to again decrease the volume, then we have to go in this direction. That means we have to give the system will, we have to give work this much amount green region. Now you can see from here that W1 minus W1, the area in the area of the region of this blue curve, blue shaded regions, is W1 is actually greater than 2 from the green region. So that means W1 minus W2 will be always greater than 0. That means if we go clockwise, we will always extract some positive amount of work from the gas. So the answer of this question will be, if we go clockwise, then we'll get some work, extract some work from this gas. So this is the, now we'll move to the these questions. That's a monotonic crystalline solid comprised of n atoms, out of which n atoms are, okay, let me do it in this solved section. Okay. So what it is asked, suppose that a monoatomic crystalline solid comprised of n atoms, out of which small n atoms are interstitial positions, means n of the atoms are in the inside of this structure of this monatomic crystal. If the available interstitial sites are n prime, then the number of the possible microstate, means out of this means there are total n prime of sites is available inside the crystal. Total n number of atoms is there in the crystal, and out of small n numbers of are there in the inside in the interstitial position. So how many ways we can do that? That is the actually total number of microstate. So let us count that things. Okay, so that means how many ways, how can we calculate these things? That means how many ways we can rearrange n atoms out of capital N atoms. This is actually nothing but binomial distribution n ways, sorry, not binomial, it's n ways. That means total number of ways we can rearrange small n number of atoms out of total n number of atoms is n factorial by n minus n factorial into n factorial. Now again, out of this n prime, so I have now n number of atoms in my hand. Now we have to put this n number of atoms in the place of n prime numbers of n prime places. So how many ways we can do that? Again, we can do that in n primes cn ways, right? So that means this will become n prime factorial by n prime minus n factorial into n factorial. So that means it's actually, so the how many ways we can do that? So nothing but if we multiply these two things, then we will get the total number of microstate. The total, what is the total number of microstate? It is nothing but ncn into n prime cn, that is n factorial n minus n factorial into n factorial into n prime factorial by n prime minus n factorial into n factorial. So that is that. So this is a very simple question. Now we'll move to the next question. I hope you guys have no question regarding these questions up to now. So I will move to the next question, which is, so this is very interesting question that I want to do. So this question, let me go there. Solution. Now this is actually very, so this is actually very interesting question. Okay. In this question, it is asked that a system composed of two states, one with energy 0 and other with energy E. If we put n number of particles in these two states such that n0 particles are there in energy 0 state, what is the entropy? Now it is asked that if there is a two state is there, suppose this state there and this is another state is there, this state's energy will be Z, this state energy will be small e. Now if there are n number of particles are there, now we have to put n0 number of particles here and n1 number of particles, suppose n0 number of particles here and n1 number of particles there. So how many ways we can do that? That actually gives me the total number of microstat. So before going to solve this question, I want to say something, that in the first tutorial, as I am saying that in the first tutorial, as I have said that there are three, means to my base knowledge, three well defined entropies are there. One of them is Boltzmann entropy. Okay, Boltzmann entropy, which actually we did in the statistical mechanics for relating the entropy in the relating the entropy coming from the thermodynamics and coming from this statistical mechanics. So these actually connect the entropy from thermodynamics and entropy coming from statistical mechanics. Now there are another notion of entropy is there, which is called Shannon entropy. This is also entropy which actually captures the uncertainty in a probabilistic event. It's actually measure the uncertainty. It's a measure of uncertainty of a probability distribution. So if Shannon entropy is, means the larger the Shannon entropy is, larger the uncertainty regarding with the probability distribution, or regarding with that stochastic, regarding with that random things, with the random events. Now there are another notion of entropy, which is actually Kolmogorov entropy. It's actually it's actually it's actually used in chaos, measure the chaotic behavior. It's actually a measure of chaotic behavior, in classical system. Okay, so that's that. Now in this question, it is very important in that sense. From this question I want to show you that this Boltzmann entropy and the Shannon entropy are actually related. They are not different notion of entropy. We can actually you can actually prove that this Boltzmann entropy and Shannon entropy, these two notion of entropy are actually same in thermodynamic limit. So we'll do that here. So first in the question, it is in the simple question, it is asked that what is the calculate both the Shannon entropy and the Boltzmann entropy. Okay, so first let's calculate the Shannon entropy. To calculate the Shannon entropy, in the formula of the Shannon entropy, so let me Shannon entropy SH. Okay, so in the formula of Shannon entropy is nothing but is summation of pi ln pi. Okay, so what is the pi? Pi will be the probability of finding a particle in ith energy state. Okay, so this is the pi is the probability of finding a particle in the ith energy state. So from, if I know this probability, we can calculate the Shannon entropy. So let's first calculate the Shannon entropy. So here the Shannon entropy, actually Shannon entropy. So let's Shannon entropy, call it S prime. Okay. So to calculate the Shannon entropy, we have to know this, the probability of finding a particle in the ith state. So here how many states are there? Only two states are there. One state with energy 0 and other state with energy E. So what is the probability that I will find a particle in the 0 state? What is the probability? Probability is nothing but, okay, yeah. So probability, what will be the probability? Pi will be simply Ni by total number of particle. If Ni number of particle is there, suppose here the Ni, not write it as Ni, it will confusing. So what is the probability that we will find a particle in 0 state? So that will be nothing but n0 by n. If n0 number of particles are there in number of particles are there with energy 0, that means out of n particle, if I just take one particle randomly and ask what is the energy of the particle, and if I just check the energy of the particle, then what is the probability that this particle will have 0 energy? That is nothing but n0 by n. Since the n0 number of particles are there, we know n0 number of particles are there in the 0 state, so that means that, so this is the probability, simple. And what is the probability P1? Simply that n1 by n1, we know that n1 number of particles are there in this energy with energy E, so that means n1 by n. So what is the Shannon entropy? Shannon entropy will be minus P0 ln P0 minus P1 ln P1, which is actually minus S prime, it is S prime minus n0 by n ln n0 by n minus n1 by n ln n1 by n. Okay, this is the Shannon entropy, nothing but Shannon entropy. So first part of the question have been solved. Now the second part, the Boltzmann entropy. Now we know that what is the Boltzmann entropy? Boltzmann entropy, to calculate the Boltzmann entropy, at first we have to know what is the total number of microstate. What is the total number of microstate? If we know the total number of microstate, we can calculate the Boltzmann entropy. Simply the entropy will be, in the Boltzmann entropy, the Boltzmann entropy will be SB K ln total number of microstate. If I take K is equal to 1, then we'll get S beta equal to simply ln lambda. So all the things we have to do to calculate the Boltzmann entropy is to calculate the total number of microstate. So let's do it as we did in this previous question. So how many ways one can put n0 number of particles out of total number of particles n in one of the state? It is very simple and straightforward. That will be S will be nc n0, that is, okay, sorry, this is nc n0, that will be n factorial by n minus n0 factorial into n factorial. So what it will be, entropy will be SB ln W. It is actually ln n0, so ln n factorial by n minus n0 factorial. Now n factorial. Now as we all know that all the things we have observed in nature is actually in thermodynamic limit. What do I mean by that word, thermodynamic limit? Thermodynamic limit here means that my total number of particles approaches infinity, means my total number of particle will be infinity, and the total number of particle that remains in zero, energy state 0, is also infinity. But the ratio n0 by n, the total number of what fraction of the particles are what fraction of particles are there with energy 0 is finite. This means n0 by n is actually a finite number. Similarly, n1 means what fraction of particles are there in with energy E is also finite. It's also finite, but both this quantity n0 goes infinity, n goes infinity, n1 also, where this limiting value is exist. n0 tends to infinity, n tends to infinity, but n0 by n is finite. Here also that. So this actually calls this is actually called thermodynamic limit. Thermodynamic limit. Okay, now we will, so this is the entropy, this is the Boltzmann entropy. Now what we will do, we basically, since we know this n tends to infinity, all the things is actually infinity, so one thing we can do, that we can approximate this ln n factorial as n ln n minus n. What this approximation is called? This approximation is called Stirling approximation. Stirling approximation. And when it is valid? It is only valid when n is very large. N is very large, then we can actually do this approximation, which is called Stirling approximation. Now since we are in the thermodynamic limit, that means all the quantities are going to infinity. That means we are in the safe hand, and we can apply this Stirling approximation. So let's do that. Ln n factorial minus ln n minus n0 factorial minus ln n factorial. So this will be nothing but n ln n minus n n0. Okay, there will be a factor n minus n0 minus, this will be minus, plus, so this is n, this is plus n minus n0 minus, this is actually n0 ln n0 plus n0. Now you can see that minus n, this will be cancelled out, and this will be cancelled out. What we left, that n. Now if we just rewrite this equation, this as n minus n0 plus n0. Now you can see ln n minus n minus n0 ln n minus n0 minus n0 ln n0. So now if I take these two terms, we will get n minus n0 ln n minus ln n minus n0, and if we took these two terms, we will get plus n0 ln n minus ln n0. So now we can write it as n minus n0 with a negative sign here, ln n minus n0 by n plus n0 ln n0 by n. Now you can see where I want to reach, right? Now can you see this, that in the expression of the Shannon entropy, exactly same looking things are there. So there it is n minus n0 ln n minus n0 by n. What it is? It's nothing but the probability of the particle n minus n0 by n, what it is? It is nothing but the probability of a particle remaining in the energy state E. So it is nothing but probability P1. Oh, so that's that. And where it is? Oh, here. Let me write it here as n minus n0 ln n0 by n, as n1 is nothing but n minus n0 n. So n1 is the number of particles remaining here. That means if the total number of particles is n, then what number of particles are there with energy E is basically simply n minus n0. N minus n0 ln n minus n0 by n. So now you can see that this quantity and this quantity exactly looking same, except here one factor by n is missing in these two things. This is by n is missing here. So here is 1 by n is there and 1 by n is there, but here the 1 by n factor is missing. Now what is the catch here? Now the caveat of these things is that in case of Shannon entropy, what we have calculated, if you remind yourself that here what is the probability, this probability is for what? The probability is for the probability of a particle, a single particle. Okay, who is there? Oh. So probability that a single particle will be at energy state 0. This is the probability of a single particle, and this is also same, but here the entropy is for total whole system, total n system. So that means this is actually the entropy of a single particle, entropy of a single particle. As I have said, what this Shannon entropy captures? This Shannon entropy captures the uncertainty. What it captures? Uncertainty. So that means it's actually telling me that if I randomly choose a particle from n number of particles, it's actually tell me the measure of uncertainty that I don't know how much I don't know about this particle. So this is actually entropy of that single particle. So we know that in the thermodynamic limit, the entropy is an additive quantity in thermodynamic limit. That means if the entropy of a single particle is there, so what will be the entropy of the whole system? So it is nothing but if we are in thermodynamic limit, so entropy is additive. So that means it's nothing but the total entropy will be, total Shannon entropy will be n, total number of particle, into s prime, which is nothing but minus into something, minus n into, so if I write it exactly here, so let me write it here, equal to minus n0 ln n0 by n minus n minus n0 by n ln n minus n0 by n. So now you can see that this Shannon entropy is actually exactly equal to the Boltzmann entropy in the thermodynamic limit. So that's that. Hence we prove that in the thermodynamic limit, the Shannon entropy and Boltzmann entropy are both entropies are giving the same result. So now you can simply from this two state to multi-state, you can simply extract the main theme, the main things here, that is that the Shannon entropy and Boltzmann entropy are same. You can actually exactly get that relation if we use m number of state instead of 2 states. Simple step is exactly the same steps will be there. Only thing is there is a not only two things, not only two step in case of Shannon entropy. This not only two step S prime, it will be I, if I state are there, I equal to 1 to m minus pi ln pi. And what will be the Boltzmann entropy? Boltzmann entropy is nothing but Boltzmann entropy will be SB will be, oh okay, let me write it first here. What is the Boltzmann entropy? To calculate the Boltzmann entropy, we have to calculate, what we have to calculate? So here it is the probability minus I equal to 1 to m. If ni number of particles are there in I state, what is the probability? Ni by n, simply ln ni by n. So what is the microstate? Microstate is nothing but total number of particles n factorial by n1 factorial into n2 factorial into dot 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 into n m factorial. What is the ni? Ni is the total number of particles that are there in I state. So it is n factorial by pi I to 1 to m ni. So that's that. Now if Boltzmann entropy will be ln omega. Now if you calculate, you will get exactly S equal to again with use of Stirling approximation, when in thermodynamic limit you will get exactly the result will be minus summation of I ni ln ni by n. You can easily read off from these two expression that the 1 by n factor is missing there, because we have already discussed that this Shannon entropy is only captures the uncertainty or the entropy of a single particle. Now in the thermodynamic limit, since this entropy will become additive quantity, then this entropy, Shannon entropy of the total system will be exactly same as the Boltzmann entropy in the thermodynamic limit. So that's that. So we have solved this question. Now if you have any question regarding this this question or the solution, you can ask me, or otherwise I will go to the next question. Okay, so if you guys don't have any question, then I will go to the next question. So in the next question, okay, next question, okay, the next question is very simple. Next question is very simple. So I will not do this question because it's very simple, because all this type of question I have did it once in the previous tutorial. Now this question is another interesting question, so I'll solve this question actually. So okay, let it to So it is asked here, the one-dimensional random walk takes step to the left or right with equal probability. The probability that the random walker starting from origin back to the origin after n even number of steps is. Okay, so let's do it. So it's a very standard question. So but I am doing these questions here because some of you guys asked me to solve different questions from that was there in the previous assignment of the course. So basically in this tutorial I am solving those questions which are not actually there in the previous year assignment of this course, Introduction to Statistical Mechanics NPTEL course. Now in the next week, from the next week, I will stick to that things that I will actually solve in the next week the previous year assignment which was given in the previous year. Okay, so this question I want to solve this question. Now a one-dimensional random walk takes steps to the left or right with equal probability, the probability that a random walk starting from origin back to the origin after n even number of steps is. So here it is been said that there is a random walker who can go right side with probability half or in the left side with probability half, both probability. Suppose he is at time t, he is in this position. Now the probability that he will go to the right, that means in this position with probability half, or he can go toward this position with probability half. Or you can think as this, the guy who don't want to move straightly, he just want to toss a coin, and if the toss a fair coin, and if the coins come up head, he will go toward right, and if the coins means if the coin is tail, then he will go to the left. This is actually crazy guy, but the question is asked such, so we have to answer these questions. So that's that. So that is thing. Only the drunken fellows are moving like this. No, no means ordinary guys walk like this. So sometimes this problem also called drunken fellow problem. So that's that. So now what it is asked, that is that now suppose that this crazy guy who just want to go from one place to one place, suppose that in the right side, suppose he want to reach from 0 to mth step, right? That means if in the total number of state n, he took n plus number of steps in this direction and n minus number of step, n plus step in this direction and n minus steps in this direction, then the total simply the since he took the total number of state n1 plus n1, okay, n1 minus simply since he took exactly n number of steps, that means the total number of steps should be n plus n minus should be n, and now he at least reaches at a step m from where he started, that means n plus in this direction, suppose in the positive direction, in the right side, so that means n plus, this is right, this is left, n plus and n minus, n plus n minus is equal to m. Now if we solve these two equations, we will get that if we add these two equations, what we will get? 2n plus equal to n plus m, that means n plus will be n plus m by 2. Similarly, if we subtract these two equations, what we will get? We will get n minus 2n minus is equal to n minus m, that means n minus will be n minus m by 2. Okay, that's that. Now the remaining question is very simple, that we have to calculate what is the probability that he reaches towards he took n steps in the right in the right hands, in the means positive direction, right, in this direction or in the right direction. So so PM will be what is the probability, we have to calculate that. So to do so, I have to remind you that it is the simple problem that if there is a coin, if you just tossed it multiple times, suppose that n times, what is the probability that out of this n times m number of head, okay, so notation should be out of n number of outcomes, means if you tossed n number, out of that n number, how many times you actually get n plus of head. So this is nothing but a simply binomial sampling problem, which actually that how many ways you can, if there is a suppose that you have a n number of combinations of head and tail in your hand. Now how many ways you can arrange, you can rearrange this n number of heads and n plus number of heads out of them. So if suppose that in your hand, suppose that n some things are there, suppose some red ball are there. Okay, let me do it this way. Suppose that in your hand n number of balls are there, some of them are red, some of them are red, some of them are blue, some of them are blue. Now I have said that in this total n number of balls, I know that there are n plus number of red ball. Now how many ways you can rearrange this system? How many ways you can rearrange this system? It is nothing but you n factorial by n plus factorial by n minus plus factorial. So that many ways you actually rearrange these n red and blue balls to get n plus in this get and the similar get n plus red balls and total number of n balls. So that's that. Now this is actually similar to this question. That means in how many ways you will get head, n plus number of heads out of n tossed. So that is actually simple, n factorial by n plus factorial into n minus factorial. Now here the color of the ball is certain. Now suppose that the color of the ball is not certain. That means what is the probability? You have to multiply what is the probability that you will get exactly n plus number of heads, or the guys actually go towards right direction, n plus step. So that will be the n plus into half into n minus, and we know that n plus into n minus equal to n. So that we will use here n plus by n plus factorial n minus factorial into this will be n plus n minus, that is n. And here if we put that thing, that we know that n plus is equal to n plus m by 2. So n plus m by 2 its factorial n minus m by 2 its factorial. It's I just put the value of n plus n minus that I have calculated here in this expression. So half n. So this is the probability that that guy actually reach mth step in the right direction. Now it is asked the probability that random walker starting from the origin, he actually start from the origins and he again back to origins. He doesn't move a single step. That means what is that value? M is equal to 0. Now if I put m is equal to 0, what is the probability that he will again after n step reach to the origin? Is actually n factorial by n by 2 factorial n by 2 factorial into half to the power n. So this is the answer, that this is the probability that if a individual just walk like this, then after n step, what is that? This is the probability that will reaches toward from where he started. So that is the answer of this question. Now let me go to the next question. Okay. Next question is, a box contains 1 mole of gas. Consider two configuration. Each half of the box contains half molecules, and each thirds of the box. So let me remind you guys the Gibbs paradox here also, because this question actually is about the Gibbs paradox. Okay. So okay, the question is, that's the question. So it's actually Gibbs paradox. So let me remind you what the Gibbs paradox is. You actually see it in this way, that suppose you have a large number of gas molecule. Now from the first things that you know, that the entropy is actually something that measure irreversibility, right? That means if you did something, but you can't reach to the initial condition, then the things is called irreversible. You can't just do the backward every things, and you can't reach to the same initial condition. That is actually called irreversibility. Now suppose there is a large number of gas molecules are there, and gas molecules are there also. Now if you mix up these two gas molecules, large number of gas molecules, now can you just separate the each and every molecules from this combination? You can't do, right? Means there is a huge number of particles are there. So if they once they homogeneously mixed up between themselves, you can't really again separate these two gases, these two gases. So that means this actually tells that every mixing means the diffusion, means that's a natural process. If you just put two gases there, they will actually mix, they actually mixed up because of diffusion, something like that. That means the natural process, that is the mixing, will always increase. The mixing always increases the entropy of the system, and that make it irreversible. That means once they get mixed up, you can't separate them out. Now the Gibbs is a very clever fellow. He just said that suppose that you have a box of same ideal gas, same gas. Now suppose that I put a boundary there, same gas. Imaginarily I just put a boundary wall between the gas, between the whole gas. So that means in my imagination, these two part of this gas now separate out. Now if I just remove this imaginary that boundary, that means these two part will be mixed up. That means this should, as from our previous explanation, since these two part mixed up, that means some entropy should increases. Okay, so it should be right, since at every case if we just if we just mixed these two parts of the gas, we can't really separate it out. But then that means entropy delta S should increase. But then Gibbs says that as this is actually similar kind of gases, every time I can put a boundary, imaginary boundary between these two subsystems, and actually we can separate it out. That means it's become really reversible. And if I just put that boundary wall, there is a two separate kind of gas. If I just take it out, they got mixed up, and again I just put it out, then I just got back my initial condition, right? So is the entropy is increasing really? So this is the paradox. The entropy should increased, by here the entropy is not actually increases. So this is actually paradox, and this is actually solved by the Gibbs. Actually the solution is actually given by Gibbs. If you recall the second lecture of these courses, Introduction to Statistical Mechanics, then you actually there is some form called Sackur-Tetrah form of entropy, where you just used that since these particles are identical, suppose that there are two red balls are there which is identical, right? If this is one in the position of 1 and in the position 2, now if we just swap the position of 1 and 2, they actually not create any new microstate. So that is actually that's actually solved this Gibbs paradox, and the Gibbs himself gave this explanation, and he actually solved this paradox by putting one things that these classically gas molecules are identical. Now what it is asked here in the question, that a box contains 1 mole of gas, consider two configuration, each half of the box contains half molecules. Each third of the one contains, means one configuration with this type of half molecules and half molecules. One configuration is that 1/3, 1/3, 1/3. Now from this Gibbs paradox we actually already know that entropy or rather the microstate, since the particles are identical, then the microstate, what it is asked, that the each third of the 1/3 molecules, which configurations have the more microstate. That means we actually know the entropy does not increase. That means that actually tells us that these two systems, which actually one half of the box contains half molecules and 1/3 of the also 1/3 molecules, actually really both has the same microstate. So that's the question. So the answer of the question will be C. Now let's, okay, how many times is this time? Now another important thing, okay, to do that, so first let me, another question I want to solve in this here, it is the Liouville theorem. Let me, it's very important. Let me solution. Now I want to do a things that you know that in the premise of the statistical mechanics we said that the total the density of the microstate remain constant, right? The microstate, what the microcanonical ensemble is constant. What do we mean by that? That we mean that if the energy of the system is constant, that means if the system can be expressed as an Hamiltonian system. I think all of you knows what the Hamiltonian system is. Hamiltonian system is basically Hence in the Hamiltonian system we can express the qi dot as del h del pi, and pi dot is equal to, okay, qi dot equal to pi dot equal to minus del h, right, del qi. Qi is the position of the particles. If there is a n number of particles are there, so the position of the ith particles is qi, and the momentum of the ith particle, position of the ith particle is py. Okay, position of the particle is qi and the momentum of the particle is pi. So that's that, and you can express the evolution of time evolution of the position and the momentum in terms of in this form. So these if you express in these terms, it's called the Hamiltonian system, and this Hamiltonian is basically nothing but the total energy of the system. Now the Liouville theorem states that if rho is the density of the phase space, then del rho del t will remain 0. What is the rho? Rho is nothing but rho is a function of these pi and qi. It's actually tells the probability of a particle remaining in the phase space between pi plus, okay, dpi dqi. This will be the probability of remaining dpy and remaining between pi to pi plus dpi and qi to qi plus dqi. So this is the probability, but this is nothing but the probability. It actually tells that what is the probability that in the phase space I will find a particle who is sitting at position qi, and at that moment it possesses a momentum pi. So that probability is captured by this thing. Now to prove these things, let us go toward from the classical mechanics. You actually prove it from the classical. That is the beauty of the thing. So to do so, let's recall the thing which is actually the in the Hamiltonian system. As if you know what the Hamiltonian system is, then you actually know in the Hamiltonian system the total volume of the phase remain always constant. That means the phase volume in Hamiltonian system always remain constant. What does it mean? It means that the total accessible volume, if I put a particle whose energy is E, then the total accessible states, that means total accessible position and momentum, if that creates a volume, simply if I just draw that, if this is energy, suppose give me an example, that suppose a simple harmonic motion which is energy will be half m omega square a square omega square x square is the position, and momentum will be p square by 2m. So in one dimension the phase space will be a sphere, right, a sphere with radius e. You can always write it as x square, okay. So this is not exactly an, okay, I am wrong, it's not a sphere, it's actually an ellipse. It's ellipse, and the all accessible x and p for which this relation is satisfied will remain on the sphere of this ellipse. Now if I know the area of that ellipse, I actually know the total volume of the phase space that is actually allowed for this system with total number of energy constant, that is actually pi ab, nothing but. So this is an example of the phase space. So if I just take this, if we generalize this concept for Hamiltonian system, the volume of the phase space will always remain constant. So let's prove that first. So the volume dV, right, what is the dV? dV will be, if suppose this is my phase volume, so how it is changing actually, this is suppose the phase volume, how it is changing. Now it's changed because with time there is a velocity. So this is suppose that this is x and this p. So if the x and p is a function of time, that means this x will change in this phase space. That means since the q dot has a time evolution, so that means q and p will change. So that means in some direction this boundary will move. Suppose that in this direction boundary will move, okay, this boundary will move. So that means suppose the area of this small thing is ds and the unit normal vector is n cap. That means what is the change in the volume is actually nothing but ds. So integration of ds, the total closed integration of ds into n cap into the velocity. Velocity means what? Velocity means nothing but x dot and p dot. So let it write in compact form v dot. So it will be, so v dot, that means closed integration of ds n cap, ds n cap dot v dot vector, v vector, which is ds dot v vector, which will be this. From the divergence law we can apply the divergence law here, and this will become from the divergence law we know that the closed surface integral can be written as volume integral, as this will be volume p dv over total volume. So there dv dt, so this v is not the actual, this is some v tilde, so total volume, and this is actually, yeah, this is again I just integrate over the volume. So these two volumes are same, but now this is the change in the total volume with respect to time. We have to integrate with differential volume. So v and divergence of v, right? Now what is the divergence here? Divergence of v will be nothing but divergence del qi dot, right? V means nothing but q and pi plus del pi dot. Now interestingly, pi dot means what? Pi dot means minus del h del qi. So if I put it there, minus del pi into minus del qi h, so this term I written there, plus del qi into qi dot means del pi h. It is nothing but del 2 del pi del qi into H minus of this is del Qi del Pi into H. So now you can see we can swap this Pi and Qi. That means this term and this term is exactly equal with this is 0. That means dV dt is always 0. Now in case of statistical mechanics, what is this volume? This volume is nothing but V is actually integration of rho into dV, right? Volume is nothing but rho into dV. In case of statistical mechanics, this actually become probabilistic. So if that becomes probabilistic, that means we have to multiply this rho with this dV. That means what it will become now, then that means dV dt will be this, in case of this is actually dPi dQi. Okay, so now dV dt equal to d, since it's integration over dQi dt, so we can write it here like this, dP dPi dQi. Hence we know that this is 0. So if we expand this, actually it will become del rho del t integration of del rho del t plus, okay, del rho del t del rho del t plus del rho del t plus gradient of rho and V, it will be del rho del t into del rho del pi dot plus del rho del qi dot dpi dqi is equal to 0. So that means this should be actually 0, which is nothing but del rho del t plus this is actually gradient of rho dot the velocity field will be 0. This is actually the Liouville equation. Actually Liouville's equation. This is actually Liouville's equation. Okay, that's that. So we have proved the Liouville's equation, which is actually a very important things in the microcanonical ensemble. When we have already did the microcanonical ensemble without knowing that this rho, the density, is actually constant throughout the time. This density actually does not change with the time. So that's that. So the Liouville theorem, we can prove it from the classical mechanics, and it actually says that in the classical statistical mechanics it should always remain constant, and it should follow this relation, which is actually called the Liouville's equation. So that's that. We have proved already the Liouville's equation, and since the time is almost we are in the actually almost end of this tutorial, so let me do another simple problem, then I will just end this meeting. So the last problem of this tutorial is that for a stable thermodynamic system, temperature dependence of the internal energy Ut is represented as, so it is actually saying that for a thermodynamic system, which of this configuration is this stable one, is actually going towards the stable. So let's recall to the lecture series where we know that entropy is the del U del T. Entropy is the slope of this curve U versus T, and we know as entropy increases with time entropy increases, my system will go toward stable equilibrium. That means entropy should be positive, entropy should increase, right? That means entropy is, if entropy is positive, that means entropy should be positive, right? For a system, entropy should be positive, entropy can't be negative. For a system, for a system in thermodynamic limit going toward means or in equilibrium, entropy should be maximized, entropy should be greater than 0. That means the slope of this curve can't be negative. So let's see, here it is positive, for here it is actually the answer of the question of the, so here let's see it, here the, what is the slope, slope actually 0 here, because you can see it here that the slope is at this point is 0, at this point is increasing, at this point is increasing, at this point is increasing. So in this curve the entropy is always positive and increasing with time. So this is the stable configuration. Now let's check whether this other configure, other U versus T curves is also represent a stable thermodynamic system or not, for the pedagogical purpose. So here it is 0, 0, but here it is negative. So entropy negative, it can't be, it can't be. So this is right, it can't be. Now here it is positive, positive, but at the end of the day it's remain it's with temperature it's become 0. So it can't be actually, because at T equal to 0 the entropy should be 0. So it is here exactly expressed by this, but it is not 0. At T infinity the entropy should something, for an infinite system. As you actually, if you can recall that in the first tutorial series, the last question is that if I have infinite number of particles are there and infinite ladders are there, if I put particle, what will be the entropy, what the is entropy could be negative or not. So there we argue that the entropy could not be negative, because if we have an infinite number of ladder and infinite particles are there to put in this ladder, the entropy could not be negative. So that means if I have infinite particle, as in case of, as in nature, so means whatever amount you can think, there are a larger, means because in, if I say some 1 semi-cube volume, inside of 1 semi-cube volume also there are larger 10 to the power 23 number of, or 10 to the power 23 order of particles are there. So the every time the particle numbers are infinite, so that means the negative, as temperature increases, the entropy should also increases. So that means it's actually not the right curve. And here it's again the entropy is negative here, entropy is negative here, so entropy is 0 here, but it's a negative, so this cannot happen. So this will be the stable configuration. So that's it. So that is for today's tutorial. In the next tutorial I will solve the question, the assignment question regarding with the third week lecture. So that's it. So if you guys have any question, so it's the time to ask me, or you can leave the meeting. Okay, if you guys don't have any question, then let me stop this meeting right now. Okay, so thank you guys for joining. So that's it.